Let's say I gave this circuit to you on an exam and asked you to analyze it. That thought might be a little disconcerting because it looks very different and unlike any of the other circuit examples than we've done thus far. Most prevalently, it has two different transmission lines. Same characteristic impedance for each, but two different electrical lengths, one lambda and one half wavelength lambda over 2. What we've done here is essentially taking these two structures and we've made a 4-port device. Port 1, port 2, port 3, port 4. And then we've connected matched, quote-unquote, matched loads to 3 of those ports and connected this matched source to the first port here. And so we have a source, it provides energy into the system, and we'll find we get voltage and currents at every location within the circuit. Now, the problem we're trying to solve is what is the value V1, shown right here, defined in this way. How would we go through and determine this analysis? We could go through, of course, and find the answer because we know the device equations, we know the telegrapher equation solution for the transmission lines. Of course, we know Ohm's law is the device equation for each of the resistors. And then all the currents and all the voltages are related by Kirchhoff's voltage and current law. So we could go through and write down a set of equations for the currents and voltages and how they are related. And from all those equations, we could slug through the algebra and finally find the answer to V1. The question, could you do that on an exam where you had a limited amount of time? Well, you could if you approach this analysis in the correct way. Notice that aside from this source here, the 4-port circuit itself has a plane of bilateral symmetry. So this is a problem that we can analyze using our odd-even mode analysis, and it becomes much simpler when we do so. One of the problems with this circuit is, you have loops in here, and so you start chasing your tail if you try to do things in a linear form. You have to just really write down all the equations and then slug through the algebra to get to the answer. But with the odd-even mode analysis, we'll find that this circuit is relatively easily determined. Now, the schematic itself is a little bit busy, and it turns out we can simplify the schematic in a way that hopefully will make things a little bit clearer and easier to handle with respect to analysis. The key thing in this circuit is when you look at the bottom conductor of the transmission line. The way that this is written or described is the gold is the top conductor, and then the bottom conductor is on the transmission line is the black conductor, and that black conductor is connected to ground. So this is basically the ground plane. If this were a microstrip transmission line, this would be the top side etched in gold, and then this would be the ground plane on the other side of the circuit substrate, which the circuit substrate helps determine the characteristic impedance of that transmission line. If we look up here on this transmission line, what I've done to try to, again, keep the schematic a little bit straightforward and keep it from getting too unwieldy, is I actually flipped the orientation of the transmission line. So the top conductor is now here on the bottom, and the bottom conductor is here on top. And you can see for this one, too, that bottom conductor is the ground plane. It's connected to ground. And that's why this voltage is oriented in this way. We have minus to plus. So the plus terminal now is connected to this 50 ohm resistor. The minus terminal is connected to ground. That is here. So these ground planes, these bottom conductors, are really sort of superfluous to our analysis. And to keep our schematic from getting, again, too unwieldy and complicated, generally speaking, will remove these bottom conductors. And this is fairly common in microwave circuits where people won't draw in the schematic both conductors, particularly when the bottom conductor itself is the ground plane of, let's say, a microstrip transmission line on a circuit board. So here is the schematic then we get when we remove the bottom conductor. So you can see it's much simpler. I've taken the 4-volt source that was up here and folded it down. So again, it makes sense plus to minus there. And you can see again that we have a 4-port device. Here's 1 port, 2, 3, 4. And all we're showing is the top terminal of those 4 ports. The second terminal is ground. And again, that's sort of implied in that schematic. And what we've done is connect a match, quote-unquote, match load to each of these ports and a match source into this port here. And again, we're trying to find the voltage that occurs here. Now, one thing to keep in mind, and sometimes this causes confusion for students, is we do have two conductors, two transmission line conductors in this schematic, but these are conductors for different transmission line. This is the top conductor of one transmission line of length lambda. This is the top conductor of a second, completely separate and different transmission line with length lambda over 2. The bottom, remember, the bottom second conductor for this transmission line is the ground plane, and the second conductor, the bottom conductor of this transmission line, is likewise the ground plane underneath. And so we look at the schematic, and this sort of has a topology that's associated with the top side of a circuit board. And we physically, if we were to build this on a circuit board, this would be the top side edge of a microstrip transmission line. The bottom ground plane would be the second conductor there for that transmission line. And we would literally go through, and we could put resistors, solder them from point to point in this way, and then take one end and go drill through the circuit board down to the ground plane below. We turn off that 4-volt source that was right here, and by saying we turn it off, we set its voltage equal to 0. V0 is a short circuit, so we just have a conducting wire to ground in its place. And the reason we do that is when we look at the remaining circuit, once we turn our source off, we see clearly it has a plane of bilateral symmetry. This is a symmetric circuit. It is a mirror image of each other across this plane. And of course, the key thing to understand here is this bilateral bilateral symmetry, this reflection symmetry plane, cuts this transmission line right at the halfway point, or moves through at the halfway point. So from here to this end is a half wavelength. From here to that end is another half wavelength. The same thing for the transmission line here. It cuts this lambda over 2 half-wave transmission line into, so from this point over here is a quarter wavelength, and from this point over there is a quarter wavelength as well. So we can go through and apply our odd-even analysis to determine this unknown voltage, V1. So let's turn our voltage source back on to its original 4 volts for e to the j0, a complex value, magnitude of 4, and a relative phase of 0 is this source voltage here. Let's turn it back on, and of course this disrupts the symmetry of the circuit. Our plane of bilateral symmetry is right here. If we were to reflect across to the other side of the circuit, what we find is there is no 4-volt source. Instead, we have a short circuit from this 50 ohm resistor to ground. All right, again, this point here reflects over here, and we're going to model that short circuit from this location to ground as a voltage source of 0 value. And of course, that is what a short circuit is. This may be the most important step of the entire analysis, is identifying where the reflection of our source ends up. If this is our plane of bilateral symmetry and reflect across that plane, that source would end up right there. So we need to put a 0-valued source at that location so we can complete our odd-even mode analysis with superposition. And this is a mistake that students make sometimes in this process, is they'll put another source down here, for example. But of course, the plane of bilateral symmetry doesn't run through the circuit in this way. It runs in this way. Or sometimes students will put a source here and here and here and here. But again, we just had one original source reflected across the plane and see where it lands. And that's the place where we need to put replace a conductor with a 0-valued voltage source. So this becomes our circuit now. 2 voltage sources that are related to each other by reflection symmetry, or at least a reflection across the plane. Again, they're not the same, so it has disrupted the symmetry, but we can re-establish the symmetry by going through and calculating the even and odd mode sources for these two. The even mode voltage source for these two is simply 4 plus 0 divided by 2, and so the even mode voltage is a value of complex value of 2. Likewise, for the odd mode, we have 4 minus 0 divided by 2. Well, that gives us the same value for the odd mode source. And this is what happens when we have a one non-zero source and the other being a 0-valued source. we find the even mode and the odd mode source values are the same value. It's simply the original source divided by 2. So even and odd mode source voltages. Now what do we do with these two values? So we go back to our circuit and we replace our 4-volt voltage source with a voltage source that consists of two sources in series, one being the even mode voltage and the other being the odd mode voltage. And in this case, so we have two 2-volt sources in series, and that of course creates then the voltage difference of 4 volts that is required. On the other side, where we had our 0-volt source, our short circuit, we replace it with, again, 2 voltage sources in series, one having the even mode voltage and the other being the opposite of the odd mode. The odd mode voltage multiplied by -1, or the odd mode voltage multiplied by e to the j pi, a phase shift of 180 degrees. And so now this is sort of our elaborate way of describing a short circuit. Here is a voltage source of 2 in series with the voltage source of -2, and that creates the 0 voltage difference from the 2 points as is required. The reason for defining these voltage sources in this elaborate way is evident hopefully when we go through and apply superposition. The first thing we do is we turn off our odd mode sources. So we had an odd mode source of 2 volts here, we set it to 0. We had an odd mode source of -2 volts here, we set it to 0. And all we're left with then is the even mode voltage source on either side. And notice these are exactly equal to each other, 2 and 2. And so what we've done is, what we have in front of us is a circuit with even mode symmetry. And because it has even mode symmetry, not only the circuit is symmetric about this plane of bilateral symmetry, the sources are likewise symmetric across that plane. That plane of bilateral symmetry becomes a virtual open. We know that no current can flow across that reflection plane of reflection symmetry, and so that is defined as an open circuit. I is equal to 0, and so there's an open circuit right in the middle of the 2 transmission lines. For the other half of the superposition, then we go and we turn off our even mode sources, set them to 0, and we turn back on our odd mode sources. So here's one odd mode source, a value of 2. Here is the other odd mode source. On the other side, notice it had the value of -2, 2 times e to the j pi, a phase shift of 180 degrees with respect to the source on the left. And because we have a symmetric circuit with a plane of bilateral symmetry, because the sources have an odd symmetry, equal magnitude, but phase shift of 180 degrees, then we find that the boundary, or this plane of reflection symmetry, that plane becomes a virtual ground or virtual short. It shorts to ground, and so the voltage at every location along this plane will be equal to 0, shorted to the ground plane. And those points include, and the most importantly in this circuit, include 2 points on each of the, 1 point on each of the 2 transmission lines, I should say. So right here the voltage goes to 0, and right here the voltage goes to 0 on these 2 transmission lines. And because we have this virtual open and this virtual ground or virtual short, we can analyze the structures relatively easily. We can divide them into 2 half structures and analyze each one individually. So here are the 2 half structures that we are going to analyze for this particular problem. Most often we analyze the half structure on the left side, that's where the original source was, but in this problem we're going to choose to analyze the half structures on the right. It doesn't matter. The reason we choose the right is because in the end the value we're trying to find is this voltage right here, and so this voltage V1, and so we use the half circuit that includes the value we're attempting to determine. So for the even mode half circuit, we call this V1E for even, and we attempt to find it by analyzing this half circuit. Notice the voltage source over here is the even mode voltage source of 2 volts. The other half circuit then we analyze is for the odd mode analysis, when we have a virtual short or virtual ground through the middle of our circuit there. And so the voltage that we try to find is V1 odd. V1 odd and V1 even most often are different values. There's no reason to assume that they would be the same. Sometimes they turn out to be, but for the most part they are different values. And the reason that they are different values is, one, the transmission lines are short at the end, and on the other hand, these are open. The other reason is because the voltage source here is a +2 to the e to the j 0, but the voltage source here is a -2, 2 times e to the j pi. Remember, this voltage source on the right side is the odd mode voltage times -1, shifted by pi radians, or 180 degrees. So make sure that you get the right voltage source here for the odd mode. Again, for the even, it's e to the j 0. For the odd, it's e to the j pi. And again, that's a mistake that sometimes students will make, so be careful when you set that up. So let's start by analyzing the even mode half circuit. We know it's even mode. We have the even mode voltage of 2 here, and the plane of bilateral symmetry now has a virtual open. So we look at the structure, and what do we make of this? What is this saying to us? And it takes a little bit of practice to understand what this means based on this sort of new notation, shorthand, where we've kind of dropped off the bottom side conductor. But what's saying here is we have a length of transmission line, that is length lambda over 2, 50 ohm characteristic impedance, that is terminated at this end with an open circuit. This is a terminated transmission line. We've done this several times, of course. When we talked about terminated transmission line, we terminated an open circuit. We know at that point that the total current must be 0 by the boundary condition that is imposed by the open circuit there. And of course, the open circuit at the end doesn't mean that the input impedance is going to be an open circuit necessarily. Usually it is not. We have to go through and take this load impedance and determine what that input impedance would be. We want to replace this whole structure with its equivalent circuit, and to do that we need to find the input impedance of this transmission line. Fortunately, in our case, our transmission line is lambda over 2. That's one of our special cases. We know that when we have a transmission line length lambda over 2, 1/2 wavelength, that the input impedance, and only for this special case, the input impedance will be equal to the load impedance. Again, generally that's not the case. The input impedance is very much different than the load impedance, but for half wavelength, that special case, it turns out to be the same. So if we have an open circuit that terminates the transmission line, and the transmission line is a length lambda over 2, the input impedance then has a magnitude of infinity. It is an open circuit as well. And so this is all replaced. You can think of it as a lumped element that comes from this terminal on one side to ground on the other, but the lumped element impedance has a magnitude of infinity, an open circuit. And so we can rewrite the circuit here with its equivalent circuit, where again now we've modeled the input impedance of this structure as simply an open circuit, since that input impedance is in fact infinite in magnitude. So this becomes our new equivalent circuit by evaluating this case. Now we have another transmission line here, and so we need to replace it with its equivalent circuit. We need to replace it with its input impedance, which will go from this terminal down to the ground plane, down to ground. So what is the input impedance of this structure? Well, fortunately, we know what that answer is. This again is a special case because its length is lambda over 4. Really, this is a special case in two ways. The transmission line is lambda over 4, and the load that terminates this transmission line is an open circuit. And we've seen this before and did the analysis where the input impedance of a quarter wave length transmission line that is terminated in open circuit turns out to be an input impedance of 0. Quarter wavelength, the input impedance is proportional to the inverse of the load impedance. Since the load impedance has an infinite size, then the input impedance will be 0, a short circuit. and that then is modeled as a lumped element, which goes from this point in the circuit, a lumped element impedance that has at one end at this point and the other end to ground, but that lumped element impedance has a value of 0. In other words, a short circuit to this point. And so the circuit now that we have, this is replaced with its equivalent circuit. This point right here now is connected directly to ground because of that input impedance of equal to 0. And so this becomes our equivalent circuit for this half circuit. And all of a sudden, this problem is looking much easier to analyze, because this looks very much like the kind of circuit that you might have had your freshman year in circuits class. And it's actually even a little bit easier than it looks, because if we notice closely, we see that this 50 ohm resistor now has ground potential on either side. In other words, the voltage across this resistor is 0. There's no voltage drop from one side of the resistor to the other. And because the voltage is 0, the current through it is equal to 0. And really, this then circuit, or this element, becomes superfluous to the circuit itself. What we have is a voltage source followed by two 50 ohm resistors in series to ground. We simply can ignore this resistor in our analysis. So that a circuit that looked so disconcerting and heinous at the beginning has reduced down to this, a simple voltage divider. Again, we've 50 ohms, last 50 ohm resistor we've left off since it has nothing to do with the circuit. We go this point directly to ground, and we have a simple voltage division problem. This is the voltage we're attempting to find, the V1. Since we're doing even mode analysis, we denote it with the superscript E to keep from differentiating it from the odd mode answer we're about to get. And since these resistors are the same value, this voltage division is very simple. It's simply the source voltage divided by 2. And since the source voltage is 2 and we divide it by 2, this voltage V1E is simply equal to 1, a complex number, magnitude of 1, a relative phase of 0. All right, now let's go through and analyze our odd mode half circuit. And again, we're going to use that half circuit on the right because it includes the voltage value that we're trying to determine. We can just determine this directly. We don't have to multiply anything by -1 when we're done. The key thing here, though, is that our source is the odd mode voltage times -1. That's where the E to the J pi, that's, of course, -1 there. So we go through and analyze this, and once again we have these structures, these transmission line structures. Both of these are terminated transmission lines. We want to replace them with their equivalent circuit. Again, this one is lambda over 2, and we've just talked about this. The input impedance for this structure will be simply equal to its load impedance if it has this length of lambda over 2. Well, the end of the transmission line is connected to the ground plane, the bottom conductor. In other words, the load impedance is 0. It's a short circuit, and therefore the input impedance is 0. This point is connected directly to the bottom conductor or the ground plane. And so we can replace this structure with this structure here. All right, the half wavelength basically has disappeared, and we have an input impedance which is the same as the load. 0 impedance from this terminal to the bottom, the ground plane of the circuit. Structure down here, again, it's lambda over 4. In this case, instead of transforming an open circuit to a short circuit as it did for the even mode half circuit, now we have a short circuit as a load, and therefore the quarter wavelength transformer or quarter wavelength transmission line will transform the load impedance of 0 into an input impedance of infinity. In other words, the equivalent circuit for all this is an open circuit, and so we'll just model with the little open terminal there, but that signifies that no current can come out. The impedance from this point to ground is an impedance that has a magnitude of infinity. All right, now if we look closely, this circuit can also be greatly simplified. In fact, analyzing this circuit is trivial, but you have to be very careful. And again, this is one of the problems students have, is when we simplify this circuit with its equivalent circuit, you got to step back and say, well, what do I have now? It may look very different after you go through and apply the equivalent circuits. So we have an open circuit at this point, but notice at this terminal, this goes to ground, and that's the most important part of the structure that is remaining. So let's stretch out this circuit that's remaining and take a closer look. The key thing to notice here is that there's an open circuit here, so these two 50 ohm resistors are in series. But on one end we have it's connected to ground. On the other end, these two resistors are connected to ground as well. There is 0 volts across these two resistors, and therefore there's no current that can flow through these two resistors either. What we have essentially, since this point is connected right to ground, is we have a simple circuit right here. The current will flow around in a loop. This part of the circuit will not be energized. Since there's no current flowing through these resistors, there's no voltage across these resistors, including the voltage V1 for this odd mode. So again, the circuit looked like it was going to be incredibly difficult to analyze, and if we hadn't used odd-even mode analysis, it would have been. But by applying odd-even mode analysis, we've reduced it to two simple circuits that we had to analyze. One being a very simple voltage divider, where we simply take the source and divide by 2. In this case, it's even simpler. The answer for this is 0, because there's no current flowing through that resistor. The odd mode voltage V1 is equal to 0. So to complete our problem, we simply complete our superposition. We simply add the even mode voltage V1 to the odd mode voltage V1. 1 plus 0, that gives us a complex value of 1, magnitude of 1, and a phase of 0. And again, it really couldn't have been simpler in terms of circuit analysis. When you first saw this circuit, it looked very daunting. And again, if we didn't recognize the plane of bilateral symmetry that could happen here, and then apply or even in odd mode sources here and here, we would have had to go through and slug through hours of algebra to go through and get the right answer. But with this bilateral symmetry, we were able to get the answer with hardly any effort at all. The key thing is recognizing where the plane is of bilateral symmetry and how the source reflects to the other side. This source reflected over here, so this short circuit we needed to rewrite in terms of an odd and even mode voltage source. Again, there were no voltage sources on either side here. If we reflect across the plane, they are not affected. The symmetry is not disturbed. It's this voltage source reflected across over here. This is where we need to do our odd-even mode source magic in order to apply our superposition. And that's the real trick of these problems, finding the boundary condition and figuring out where to add in the odd and even mode voltage sources. Usually after that, the circuit will simplify very quickly and very easily.